Okay, so let's continue from where we were yesterday. Yesterday we talked about geodesic congruences and time-like ones as well as null congruences. And in the context of a null congruence, we found that a nice way to find such a congruence is to consider the integral curves of the normal to a null hypersurface, because this normal happens to also live in the surface. Okay, so the theorem which we wrote yesterday but didn't prove was that the integral curves to a of the normal to a null hypersurface So what are integral curves? If I have a vector field and I follow that vector field, that's what is called the integral curve. If you want an example from physics, when we draw lines of force around a magnet, there isn't any real thing lying along these lines. What there is only is at any point I can place a compass and find out the direction of the magnetic field. And with that, if I can also measure the magnitude even better, and then I can draw an infinitesimal vector, which is the direction of the field, the value of the field at that point. Now, when I connect all these measurements in the sense of calculus, that I do it continuously, infinitely many times, then I get what is called the integral curve. So I have a differential equation, I integrate it, and I get the curve. So the integral curves of the normal to a null hypersurface, of course, they are null because they are the integral curves of a null vector, but they are actually null geodesics. That was not obvious and needs to be proved. This part is obvious, but conveniently they turn out to be geodesics, and therefore they define a geodesic congruence. Okay, so to do this, to prove this, let's assume that the null hypersurface, is given by an algebraic equation So in general, one way of defining surfaces or hypersurfaces in a manifold is to give one equation. You're familiar with the equation. Let's just write an example here because we'll use it to make some point in Euclidean 2 space. X squared plus y squared minus 1 equals 0. Is f of x and y, and of course this defines a circle of radius 1. Okay, now given this hypersurface, in this case it's not just any hypersurface, it's null because we are in the Lorentzian signature space-time. And now what is the normal? So earlier we were talking about defining a surface by specifying what is its normal vector. Now we are going to define the surface by an algebraic equation, one equation, so that it's a hypersurface, and now we should be able to find its normal vector. So what is its normal vector? Its normal vector is just v mu equals del mu of f, the gradient, d-dimensional gradient of f. Okay. This is a standard thing, but again, let's try and work that out in the case of this circle. So what is the gradient of this? di of f is the vector 2x, 2y. right? Di means d by dx and d by dy of f. It's the gradient of this function. So d by dx of it gives me 2x and d by dy gives me 2y, right? So what is this vector? 2. So it's twice of x comma y. Here's my circle of radius 1. Okay, and at any point on it, the vector x comma y is simply that, is the outward vector. That's the normal is always given by this construction, that the gradient of the function specifying the hypersurface defines a vector, and that vector is normal to the hypersurface. It's very easy to establish that it's in fact normal.
This outward vector, right? Is there a way to also?
No, it could be inward. No, I could put a minus in front. There's no sense of direction. This is to, I could have defined my f of xy to be minus x squared minus y squared plus 1. Not going to change anything. There's no direction associated to it. I mean, there's a direction, but there's no sign of the direction. Outer ring is the same. Now, however, coming back to this, that was just a side example. Oh, maybe I should say one more thing. The surface is smooth, this hypersurface is smooth if del I of f is never the zero vector. Okay, and if you want a nice example in Euclidean geometry, consider instead of a circle, consider a hyperbola, x squared minus y squared. So f is this now, x squared minus y squared minus 1. So for this to be 0, we have this. So we have this kind of shape, I believe. Am I right? So y, no, other way around, I think. Sorry, which way is it? This way or that way? My drawings are anyway very bad. Yeah. So x can never be 0, so it should be this one. Good. Now this one again has its normal vector, just how you would expect, by taking the gradient 2x and x and minus y is the vector in this case. That's why here where x and y are both positive, it's pointing along negative y because that's minus. Okay. But now supposing I change my function to this, f is just x squared minus y squared, and now the surface is not that, but it's a pair of straight lines. Okay. Now as a submanifold, this pair of straight lines is not a smooth manifold because there's a point, the origin, where it doesn't have where it's not a subset, near which it's not a subset of Euclidean space, because there are two different branches which meet there. And that is seen by the fact that at this point, this vector is 0. Okay, so what's actually happening in this case is that this vector is maybe large, smaller, smaller, 0, and then again, like this, but it also goes along these directions. But it does vanish at a point, and that's a singular point. So we learn that this cannot be the 0 vector. That means all components cannot be 0. Okay. Secondly, this is going to be a null hypersurface defined by that. That means this should be null. Okay. So v dot v is 0. Very good. Now, of course, v equals this is not the most general normal I could have. It is an example of a normal. What I could do is to generalize it by writing v is equal to some function h of x times the gradient of f. This is still null and it's still normal to the hypersurface. So this is more general and it can be useful in some situations, but we'll just pick this one to be our normal for the calculation. Okay. Good. Okay. Now, so this is true on n. N is my null hypersurface, given by f of x equals 0. Now, because of this, I can take the gradient of this function. Okay, this function is 0 on n. Therefore, by the same logic as before, the gradient of this function, of course, it will be in many directions. I mean, it has components in many directions, but it will have a part which goes out of the manifold. That's the one which will be non-zero. In fact, this will also be a normal. The same story. V dot V is vanishing on the hypersurface. Therefore, the gradient is a normal to the hypersurface. Okay, this is actually ordinary derivative, but we can use ordinary or covariant. They are the same for a scalar. Okay. So, since this is also a normal, it must be proportional to the previous normal V. There's only one normal to a hypersurface. Okay. So we learn that I'm going to call this because I'll be expanding, I'll be using chain rule, and when I use it on vectors, then I want it to be the covariant derivative. So we learned that gradient of V dot V is equal to some function which I'll call twice J of lambda times V nu. So gradient of V dot V is a normal, hence proportional to V, and that gives me this equation. What is lambda? Well, basically it's a parameter, not necessarily affine. We don't even have a geodesic at the moment. It's just a curve. It's a parameter along any curve that runs on that hypersurface. Okay, now let's expand this. So this gives me V mu del nu V mu twice is equal to twice J of lambda V nu. Okay, now we need one more property. Now we plug in the fact that V mu was gradient of a function. This much is true for any V which is null, but now it's gradient of that function f which defined the hypersurface. And we have the property that if you take the gradient of the gradient, well, first one was ordinary derivative, of a function and subtract the other way around, you just get 0. That's because the ordinary derivative part commutes, two ordinary derivatives commute, and the extra term is an affine connection with the lower indices nu mu, here mu nu, but it's symmetric, so those two terms cancel. Okay, because of this, I can replace del nu in, so this equation, I'll drop the factors of 2, and now I can replace this gradient nu of V mu by the other way around because of this equation. So therefore I now have V mu gradient mu of V nu equals J of lambda V nu, and of course this is the geodesic equation. So this is the proof of our theorem that if you look at the integral curves of the null normal to a null hypersurface, those integral curves are automatically null geodesics. You don't need to specially construct null geodesics, just do the procedure and what you get are null geodesics. Of course, they come out not necessarily affinely parameterized. If they were affinely parameterized, then this term wouldn't be there. But if this term is there, it's fine. We know that we can affinely parameterize any geodesic, and all we needed to know was that it's a geodesic. That was not given to us. Okay. Are there any questions about this proof? Okay, there are some other few small comments. So I think the main important one is that if n is the null hypersurface, then I think I made this comment once before, but here we have essentially proved it. It is, so we can think of it as follows. This is no longer my manifold. Sorry, I use a, so okay, let's draw it like this and I'll call it N. So we've just argued that it's ruled by these null curves which form a congruence, which we can, so if we start at a point in the hypersurface, then the integral curves will stay in the hypersurface and they'll be null geodesics. So what we can do is, each of them comes with its parameter lambda, so we can choose lambda as a coordinate of this null hypersurface, and then there will be d minus 2 directions transverse to that lambda, and these I'll call xa, where a goes from 1 up to d minus 2. And these, you can already guess that they must be space-like. We already argued this last time, because one null direction is in the hypersurface. There's also a null direction that points out in the geometrical sense, or which is linearly independent, which is not a linear combination of anything in the hypersurface. That's the u direction. Once we have two null directions, we can't have any more time-like directions, because two null directions when combined give me one time. If I had a third one, I could get more times, but my signature is only minus plus plus plus. So everything that's left must be space-like, and so these are actually space-like. I think we'll see this more precisely later on.
So these xa's are not in this hypersurface?
They're very much in the hypersurface. They're coordinates of the hypersurface. I just said that.
Yeah, so how is it space-like, since it's in the null hypersurface?
What's the definition? Go back to the definition. What is the definition of the null hypersurface?
I mean, you take any vector in that surface and then dot it with itself, it will give you a...
That was not the definition, you've forgotten it. The definition is that all vectors in that hypersurface are orthogonal to a given null vector. The given null vector is V. Therefore, V in particular is in the hypersurface. But any space-like vector which has no you can pick a basis of space-like vectors which are all orthogonal to V. They'll also be in the hypersurface. I gave you a concrete example for this reason last time, which is, imagine, okay, maybe I didn't write it, it's in my notes. In Minkowski space, you can make this construction. You can choose V to be 1, 0, 0, 1. You choose U to be 1, 0, 0, minus 1. And you choose XA to be 0. This is only for Minkowski, but it should give you the intuition. 0, then 0, and somewhere in the middle you put a 1, and then all zeros. Okay, this is the 8th place.
A runs from 1 to d minus 2.
Sorry?
A runs from 1 to d minus 2.
D minus 2.
Yes.
Mu runs from 0 to d minus 1.
Mu runs from 0 to d minus 2.
Yeah, so this entry is 0. This is 1, 2, 3, 4. This is d minus 2. This is d minus 1. So the XA have to live in this. This is Minkowski again. Please don't generalize. This is not always how this thing works. We might be in a curved manifold where coordinates could be more complicated. I'm just showing you how a null vectors work. Here is a null vector which is dotted with itself, gives me 0. Here's another null vector dotted with itself, gives me 0. The dot between these two is not 0. Okay? And here's one which dotted with itself gives me 1, so it's space-like. Okay? And dotted with either of these gives me 0, so it's orthogonal to both of them.
So it's there has to be just one null, like, and then the other can be space-like.
Has to be space-like,
Yeah,
not
has
can
to
be.
space-like.
Yes. Yes. In the null hypersurface, one direction is null and the others are space-like. That is correct. Good. Okay. So now, this null hypersurface thing was a digression, and we'll come back to null hypersurfaces often. let me just make one comment, which is that if we have, so the good situation, we always try to achieve this situation, and in fact we always can, two null vectors u, so we can construct two null vectors uv such that, in fact we will give a construction in a minute, such that u squared equals v squared equals 0 and u dot v equals -1. Just one tangential comment. Because of this relation, there is no way to normalize u. If u squared is 0, 100 times u squared is also 0. This one at least gives us some amount of normalization, because if I change u or v, then this will change. But I could change u and v by equal and opposite amounts. By the way, that's called a Lorentz transformation, and that's when this will be preserved. Okay, that's how Lorentz transformations work. If you go back to your special relativity and think about Lorentz transformation in terms of two null coordinates u and v and all the rest space-like, everything will become very simple and you will be able to understand it and also follow this better. Okay, so and then the remaining directions are null, are space-like. Now an interesting thing is, you can make two null hypersurfaces. Because for any one of these u or v, I can make a null hypersurface. So let's make one for which v is the normal, which means v is actually running along it, as we saw. Let's make another one for which u is the normal. It's a different surface, right? Clearly. I'll write like this. So I have two null hypersurfaces, one for which v is the normal and runs along it, one for which u is the normal and runs along it. What is the intersection of these two hypersurfaces? D minus 2 dimensional. And what type of surface will it be? What type of submanifold? Space-like, exactly. And in fact, in that example, it will just be the manifold spanned by only the x's. Okay, so intersection is space-like. This is very nice, because this gives us a way to think in general about null, about Lorentzian signature spaces, space-times. Namely that a natural, of course there is no unique choice of null directions, because I always have to pick a space direction to combine with time. There is a unique time, but to make a null direction I have to put in one space direction. That's up to me. So it's not a Lorentz invariant breakup, although the formulae will be Lorentz invariant once I choose my null direction. So we have to be more careful, but you can make two. If you have any vectors u and v with those properties, then you automatically get two null hypersurfaces, and then their intersection is guaranteed to be space-like. Okay, and so this is the structure you should always keep in mind when thinking of space-times and null curves. Yes?
Are there two families of these null hypersurfaces? Can you think of it?
Yeah, I mean, of course there are, because if I, a hypersurface is codimension 1, right? So I can imagine, so how to say it? I mean, just think of an ordinary hypersurface, just think of a space-like hypersurface, which is has a time-like orthogonal vector. So I can have, at time equals 0 I have a hypersurface, at time equals 1 I have another one, just a copy of the previous one. At any time I have a hypersurface.
But that's just, that will lie in just one family.
Yeah, exactly. So these if I stack them along the u direction, will fill the whole manifold. These also, if I stack them, will fill the whole manifold.
Can you do some kind of transformation for a vector to go from one null hypersurface to the other null hypersurface?
I don't know what that means. What do you mean by transformation?
I mean, is there some kind of transformation which takes you from one hypersurface to the, like, which rotates?
Just replace u by v everywhere, I guess. Anyway, let me move on. Good. So now our next goal, so now that we finished talking about null hypersurfaces, I'll just tell you that they will keep occurring again and again in the context of whenever we want to study light rays and specifically when we want to talk about black holes. Okay, not all of what I have done here will be used immediately, some of it will, some won't. So now back to geodesic congruences, and again I'm going to go back to the time-like case, so time-like congruences. Okay, now for a time-like congruence, a helpful way to think of it is the following. First, let me remind you that a congruence is a family of geodesics such that through any point of an open set in space-time, exactly one geodesic passes.
So is it possible to have time-like and space-like congruence on the same?
Time-like and space-like?
A congruence on a same.
Congruence on the same?
Same open surface.
Yeah, sure. There are different congruences, but you could have time-like or space-like or null. Open set is just a part of the manifold. You can have anything on that part of the manifold. In fact, it could, in principle, that open set could be your manifold. We have some prejudice that space-time should be so big, but if you're willing to make your space-time little but finite, you can do everything which you can do on a big space-time. Everything you do locally, all equations which are local, you can do on any open set. Yes?
So can you just draw that picture in, let's say, 2 plus 1 dimensional Minkowski space?
Okay.
The two hypers.
Yeah. All right. So, good. So then, yeah, let's do it. Okay, I think that's a good idea. So, here's x, here's y, here's t. Now, along the, so now let's ask what is the hypersurface. So first let's find a null vector. So let me draw this one and I'll call it v, which is basically along, so it's x plus t up to some normalization. And why I have to tell you what is, so it's not, I've not given it as a vector, I'm giving it as a coordinate, but I could say that this is lambda, lambda 0. Lambda is the parameter along it, x is equal to y. So it's in the xy plane at y equals, xt plane at y equals 0, and that's one of them. That's v. Now let's find u. So u, I will, u needs to have a dot product -1 with, okay, so the problem here is, I think I'll just give you the vector. I mean, the lambda will just give you the point on that line, but the vector is 1, 1, 0. In fact, it's most convenient to normalize it by 1/√2. And now, u, u should be, no, this is, no, I've got somehow confused on this point. Yeah. So, V is that, and the null hypersurface, okay, I think I said may have said something now. V is that, the null, what is the null surface orthogonal to V is vectors V as well as 0, 0, 1. So it is the V, Y plane. So V and Y, the plane generated by V and Y. Yeah. And I guess what I'm trying to see, good. No, I think I was okay. So this is also like this. This is minus 1, 1, minus 1, 0. This dot product is minus 1?
Yes.
Okay, good.
Okay, so my main confusion was that, so once V is given, then U is fixed. I was worried that the V surface could be like this and the U surface could be like this.
Yeah, no, once V is given, U is fixed.
That doesn't.
And in fact, now if you see, so if you intersect the surfaces normal to both of these, you only get points 0, 0, 1. And that's the y-axis, which is perpendicular to both of these null hypersurfaces. And that y-axis is my d minus 2 dimensional intersection of the u and v hypersurfaces, exactly. And it's space-like very clearly because it's only y direction. Yeah. Thank you. That I think illuminated it. But this example also shows that it's hardly unique. You could have picked any u and v. You could have picked u and v to have this component in the y side or even partly in x, partly in y. But whatever it is, there will be one residual space-like direction which will be normal to both u and v. And that one is d minus 2 in this case. Good. Okay, so now we are back to time-like congruences, and now we are going to study their properties. We only defined them. Now we want to actually study what they do. First, let's give one helpful observation. I was in the middle of it and then sort of got interrupted with a good question. There's always a geodesic that passes through any point in an open set. So let's suppose I'm in that open set, and let's look at a space-like, arbitrary space-like hypersurface. So space-like will be everywhere space-like. That means its normal is always time-like. I should have given you this definition last time or the time before and I forgot. A space-like hypersurface is one whose normal is time-like. Time-like hypersurface is one whose normal is space-like, and a null hypersurface is one whose normal is also null. Okay, now given that we have a space-like hypersurface, first of all, I suppose you understand the importance of a space-like hypersurface. If this time-like direction is actually identified with physical time, then a fixed time surface is the same as a space-like hypersurface. So any physical system is always has an initial state at an initial time and then evolves. So the space-like hypersurface is where you fix the initial state. That's the central role of this concept in all of physics, and we are going to use it both in the time-like and null case because we need such a space-like hypersurface for certain things. Now I am in the time-like geodesic congruence, and my point is, let's consider an arbitrary point in the space-like hypersurface, and let's assume this is all inside my open set. Oh, I'm doing all this inside. I could have a space-like hypersurface in the manifold, and I'll just consider the part which is inside O. Alright. So there must be a geodesic passing through this point. Can that geodesic also pass through another point? The problem is that the geodesic is time-like. So it's not going to be able to pass through another point. Okay, now I'm getting into an issue which I wanted to discuss later, which is there could be topologies, weird topologies where this could happen, but let's assume now that it's not going to happen. In that case, what happens is that a time-like geodesic intersects the entire space-like hypersurface at only one point. If it intersected at more than one point, then it would connect one point to another. And that's the kind of thing we are not going to allow. Because it would eventually lead to closed time-like loops. So that means that a space-like hypersurface, every point of it can be thought of as the point where a geodesic from the past, time-like geodesic from the past, cuts it and then moves into the future. If I was living on the geodesic, I would keep a clock on with me, and at this point when I hit my space-like hypersurface, I would set that clock to 0. And everybody could do that. Good. Okay. So this is a useful thing just to keep in mind. Now we are going to use proper time because these are time-like geodesics, so the affine parameter will be tau. And the tangent vector to each geodesic, as always, is nothing but dx mu by d Now let's define the gradient, a tensor which is the gradient of this v. So I'll define it with lower indices, and I'll define it to be the gradient in the new direction of v in the mu direction. Yes?
So, is a space-like hypersurface called a Cauchy surface?
It's not necessarily a Cauchy surface. That has, well, actually, I think implicit, there's a point when I will explain Cauchy hypersurfaces in detail. I think fundamentally you're right. The difference is that to have a Cauchy hypersurface, I should have a guarantee that every geodesic passes through it. Here I was simply saying that there's, for any point on it, there's a geodesic which passes through it. What we, when we study Cauchy hypersurfaces, we'll insist that there cannot be a geodesic which cleverly goes around the space-like hypersurface somehow. It has to hit it, either in the future or in the past, but has to. That's an extra requirement, and that will take much more formalism to develop, so we'll do that later because it also brings in topology in a more serious way. Okay, so B mu nu is the gradient of my vector field tangent to my geodesic, time-like geodesic. Okay, this is a very important tensor. I'm not going to go into why, but it's called the extrinsic curvature. Okay, let me not even mention that here. I think I would need to say more about extrinsic curvature, but never mind that. Here is just a tensor which we are going to use to define various things. Okay, notice that there is no reason why this should be symmetric or anti-symmetric. It's a tensor of no symmetry. Okay, but it has some interesting properties, one of which is that if I take B mu nu and dot it with V nu, I get 0. Why? Can you see why? Geodesic equation affinely parameterized. Once more you see that all the formulae are much nicer when you are affinely parameterized. Otherwise you would have got something. So because of affine. But the other property is that V mu nu, V mu is also 0. This is not a symmetric thing, so dotting with the second index and dotting with the first index are different. This is also 0. Can you see why? It's a different reason, but also one which you know. No, V dot V is fixed. V dot V is constant. In an affinely parameterized geodesic, V squared is constant. So the gradient of V dot V is 0, and that's this equation. Good. Okay. Now what we are going to do, and we are going to explain why it's useful, is we'll define something like a metric. Remember, I'm working in very abstract space-time, so I have not chosen coordinates and I have not assigned any special properties to it. But we are going to define a new metric, or a kind of metric, which will be the given metric on this manifold plus V mu, V nu. It's something we can do if we have been given a metric as well as a vector field, and because there's a geodesic congruence, we have been given a vector field. Okay. Now it has a name, and we'll justify that name repeatedly. It's called the spatial metric. If you want some intuition, I think you can sort of figure it out. Supposing this was Minkowski, eta 0, 0 would have been -1, but the time-like vector in Minkowski is 1, 0, 0, 0, 0. So this is V0, V0 is 1. So therefore this H00 is 0. On the other hand, the other components Hij are the same as Gij because this has no components in any other direction. This is all for Minkowski. So you can see that this, adding this, just removes the time contribution to the metric. It makes it singular also, but you can drop that direction, then it will be non-singular on a one lower dimensional space. So that's what you would like a spatial metric to be. Except here, we've done it abstractly with just given a time-like vector field and the original metric. We didn't use coordinates. Okay. Now, this has the property that if I, so this of course is now very clear. What happens if I dot h mu nu with my vector field? Okay, so the first term coming from here is v mu. The second term is v mu, v dot v. But v dot v has been chosen to be -1, so this is 0. This is another way of seeing why it's called the spatial metric. It's a metric that if I dot it with the time-like vector, it just gives me 0. Okay. Now we can do one more thing with it. We can define h with one index up and one index down by taking the original metric and using it to raise the first index of h. The advantage of defining this quantity is that now it's like a matrix. You can multiply it by itself because you have one up and one lower index. So if I have two of them, I can just multiply. And let's try it. So let's do h mu lambda, h lambda nu. And it's a very simple exercise that the answer is h mu nu. If you want, we can just, to see this, we can just expand this out, put the definition of h here, then you'll get delta mu nu plus v upper mu, v lower mu, nu. Okay. Now if I square this, I get the square of this, which is again delta. Then I get the square of this, which is minus vv, because I have v mu, v lambda, v nu, and v lambda is -1. So I get minus v dot v, and the cross terms are both v dot v. So I get twice plus twice v dot v. So I just get back 1 plus v dot vv, which is h again. So it's an easy exercise to show this. Good. Now, what kind of matrix satisfies this relation? Projector. So this is a projection operator. And what do you think it projects onto based on all this discussion? Space. Good. Very good. And what would you expect the trace of this H to be? The trace of the, if I take the metric and raise one index, I get the Kronecker delta. And if I equate those and sum, I get d, the dimension of space-time. But here, if I calculate the trace, I get d minus 1, which is the dimension of space. So you can see how beautiful this whole construction is. All I need is a time-like geodesic congruence, and I have constructed a lot of things which make it look like a time versus space decomposition. We shouldn't be too hasty. It may not be perfect, and it, of course, it will be very much dependent on where I am on the manifold, because this V is not just 1, 0, 0, 0. It is something which will vary depending on how the manifold metric is. Okay, good. Now, using H, I define the following quantities. They're very famous. One is called theta, and it is the H trace of B mu nu. So you can say B upper mu nu, H lower mu nu. So these indices are raised using the original metric, but then I contract it not with the metric but with H. Of course, you can easily find a simpler formula for this, because this is V is del mu V mu, and then here I have G mu nu plus V mu V nu. But as you can see, the second term doesn't contribute, because this is V nu del mu V mu, which is again vanishes by geodesic equation. So it's actually nothing but the divergence of my vector field. That's a simpler way to define theta. Now, divergence of a vector field, we often teach in school that it's del dot V and we stop there, but it really tells you how the vector field diverges. There are field lines, and when they diverge, when this is positive, they'll diverge. Okay, so it really tells you something very physical or geometrical about the field, and so that is theta, and its name is geodesic expansion. It's not just any vector field here, it's the geodesic tangent vectors, and so this is the geodesic expansion. Okay, the next one I'll define is sigma mu nu. To define this, I'll take B and I'll symmetrize it. So symmetrized B is defined as half of B mu nu plus B nu mu. Also, let's define the antisymmetric one. Okay. So here I have taken the symmetric part, but I am going to subtract a piece proportional to theta with this coefficient. So first of all, this is called the shear or shear tensor. It is obviously symmetric by construction because both terms are symmetric, but it's also traceless, because the trace is already sitting here. Trace of this is d minus 1, which cancels that. So it's traceless. So all we've done is take a generic second rank tensor and decompose it into three parts: the trace, the traceless symmetric, and the anti-symmetric part, which is already automatically traceless. So that's the last one. This is anti-symmetric B mu nu, and this is called the rotation or vorticity. That's this, and that is shear. Now why are we doing all this? Just to remind ourselves, we are doing all this in order to express properties of the geodesic congruence. And we'll find equations obeyed by these things, and they just follow from the definition. There's not any special content in them. They are just relations among geodesic properties of geodesics, but when applied in certain situations, they will turn out to have a content. Okay, one little exercise, I guess it's pretty trivial, is that since B itself had vanishing dot product with the V vector, we have sigma mu nu, the shear when dotted with V is 0, and the rotation when dotted with V is also 0. Because B was 0 when dotted with this, and the H mu nu part also is 0 when dotted with that. Okay. Now supposing I knew these three quantities, sorry I wrote them quite far apart, let's see them all together: theta, sigma and omega. Then I can reconstruct B because I've taken B and pulled it apart in three different parts. So B is actually nothing but 1 over d minus 1 theta h mu nu plus sigma mu nu plus omega mu nu. So this is the expansion, the shear and the rotation. Now we'll get a useful formula if we take B and trace its square. So trace of B squared, you can easily work out the formula. You'll see that if I take B squared, let's square this term, I'll get square of 1 over d minus 1, but trace of h squared is trace of h, which is d minus 1. So I'll have a net 1 over d minus 1, and then here I'll get theta squared. For the second term, I'll simply get trace of sigma squared. For the third term, I'll get trace of omega squared. And because of the way I've constructed it, there are no cross terms. All the cross terms vanish. The trace of this times this is obviously 0 because one is symmetric, one is anti-symmetric, like that. And h with sigma is 0 by tracelessness, h with omega is 0 because h is symmetric, omega is anti-symmetric. So all cross terms vanish. So that's it. Okay. Good. Now to derive now we can derive the Raychaudhuri equation. And the derivation, so there are many derivations. This is the most coordinate independent. He himself used a special set of coordinates called synchronous coordinates, which are very nice, very physical, very intuitive, and we'll use them but later in the course. But right now, it is his equation, but I'm not doing it to ascribe any physics outcome to anything. If you have been paying any attention, you would have noticed that we haven't used Einstein's equations or even written them down since this course started. So we don't know what's an energy momentum tensor or anything. So these are just equations about geometry, and we are going to leave them like that till we reach the time to discuss their physics, which will need much more preparation. Okay, so what are the equations for? Basically, we take B, which we have now done a lot of work to establish a lot of properties of it, and once more we calculate its covariant derivative along a geodesic. B itself was a covariant derivative in nu of the vector field, and now we are going to transport, not parallel, we are going to transport it along the geodesic. It will do whatever it does, because it's already defined in terms of known quantities, we have to find out what it does. So there's a nice set of manipulations. First we'll write this, V sigma gradient sigma of del nu, this is the derivation, this is the definition. Okay. Now we are going to use the following fact. If I have gradient in sigma times gradient in nu, I can interchange the order at the cost of a Riemann tensor. So there's a commutator of two covariant derivatives gives the Riemann tensor. So I can write this as V sigma del nu del sigma V mu. No, this is not what I want to do first, sorry. First I'm going to use a total integration, I'm just going to use a distributive property of differentiation. Let me copy it from my notes, otherwise I'll keep messing up the indices. First of all, in my notes this index is rho. Okay, so this I'm going to write as, yes, V rho, sorry, I will commute the derivatives. I think it was the indices which were making me crazy. So I'm reordering this like this. And the cost is one Riemann tensor, and that term is sigma mu nu rho V sigma. So first step is commute covariant derivatives. You get the opposite one, and this is the Riemann tensor term. Okay. Now in the second step, which I was trying to do first, which was messing up my life, I'll write this as, so now notice there's a V rho here and a del rho here. So I'm going to take this del nu out. V rho, del rho V mu. But there's an extra term in this where this should have acted on this. I have to subtract that. And finally, I write the last term as it is, unchanged. Minus V rho, V sigma, R sigma mu rho. Is this step clear? Okay, now of course it's clear why we did this. I find geodesic, I finally parameterize geodesic. And what is that term? It's just minus B nu, rho, B, yes, mu rho, rho nu. Yes. So this is B mu rho and this is B rho nu. And minus ditto. Okay. Now we can take this equation. This is like a master equation. Let me just write out this term again. This is like a master equation, and you can extract three equations from it by taking the trace of B or the symmetrized one, which is traceless, or the anti-symmetrized one, and you will get equations for this change of that quantity. Now, I should have said right away that this left side is nothing but the covariant derivative along proper time of B. By definition, because I am just taking the derivative along a geodesic which is parameterized by proper time. So let me just take the trace and I will find, now the trace is a scalar. Remember that to take the trace I want to take the metric in, but taking the metric in will always commute with this derivative, because the ordinary metric commutes with covariant derivative, and V can be taken in. V is also in the metric, because the metric is H mu nu, which is G mu nu plus V mu V nu, or I can take the trace with G, but it doesn't matter, because if I take the trace with H, then the V which comes in also by geodesic equation doesn't care. So it's either way, the trace can just be taken through this equation. And what we find is this becomes theta, the expansion. And for the expansion, I don't have to write a covariant derivative because it's a scalar. So it's the ordinary derivative. Here I get minus trace of B squared. And here, by contracting mu with nu, I have got the Ricci tensor but with the opposite sign. I did something wrong. Somebody should have stopped me. I lost a sign somewhere. R sigma. No, this is correct. This is with a minus sign, right? Arg. I have some sign issue in my notes. I definitely have a sign issue in my notes, and I won't be able to resolve it now, but I think this should be plus. Let me tell you for sure next time. Let's just hope that these are all plus. If I take the trace in these two indices, I get minus of the Ricci tensor. So now it's minus, and I get R sigma rho V sigma V rho. And this is the Raychaudhuri equation. but I can make it more detailed because I worked out for you trace of b squared a little while back. So it's minus 1 over d minus 1 theta squared. So theta dot is minus a constant times theta squared minus trace of sigma squared minus trace of omega squared minus r. Now I can change the indices to just simplify this way. If there was a special coordinate system, and there will be eventually, where v is just 1, 0, 0, 0, then this will be the 0, 0 component of r, the time component.
Are all the minus sign telling us something?
Yes, absolutely. But it's not obvious what they're telling us. First of all, let's do it one by one. There are 4 terms. This term is definitely less than 0. Okay. Sigma is a symmetric traceless tensor, and the trace of its square is also less than, minus the trace of its square, also less than 0. What about this one? It's traceless, but I'm taking the trace of its square. That's not 0. But what sign is it? So it helps to be very careful here. Omega squared is the matrix, mu is the matrix omega mu lambda nu. Right? Now, the trace, therefore, nu is identified with mu, so I put mu here. But this is equal to minus omega mu lambda, because I have to interchange mu and lambda so that this is the same as this, just the raised version. And this is the quantity which is positive. Okay? So, in the end, this quantity is actually, so trace omega squared is negative, so this is positive. So let's rewrite this therefore as minus 1 by d minus 1 theta squared, that sign is good, minus, so here we'll just write it as sigma mu nu. And this one being symmetric, I believe we can argue it is symmetric and traceless, should be arguable that this is positive. That means it's negative with this sign. The next one is omega mu nu, but with the plus sign because of this calculation. So this is not giving us a negative sign. The last one, what sign is it giving us? Well, the answer is that we have no way of knowing because we haven't said anything about our space-time. There are space-times which have vanishing Ricci tensor, there are space-times with negative Ricci tensor, positive Ricci tensor, all are known. Okay? So, there's nothing you can say. Therefore, although it looks like the signs are telling us something, that's only going to be true if I can somehow get rid of this term and I can assign a sign to this term. And this one we can easily do. So there's a result, I think I'm not going to prove it here, which says what? Sorry, I don't know why I said something silly earlier. It's this, is this positive or it's not positive?
It has to be positive.
No, but supposing this is, supposing we were in Minkowski space and this is 0, 1 and this is also 0, 1, then this has the opposite sign. So not necessarily. But this one should be positive, sigma mu nu. Even that I'm not sure why. Sorry, having a bit of a, anyway, we'll worry about it later. We're not going to use any sign of it now. What did I want to say? That one can set, so if the congruence is hypersurface orthogonal. Last time I used this concept, but only for null geodesics, but you can use it for any geodesic. time like geodesics also, basically means that the geodesics don't just cut my space like hypersurface, but cut it orthogonally. And I can choose a congruence to be like that. Then this quantity omega mu nu is 0. So by a convenient choice of the congruence, I can make omega mu nu 0. So that term I don't have to worry about, and in fact, generally we don't worry about it. But this term I can't do anything about. This is a property of space-time. Sure, I can choose V to be some time-like killing vector or another one, but it's time-like, and so something about this Ricci tensor it needs to be known before we can say anything about it. Okay.
What is the definition of hypersurface orthogonal?
Yeah, in this case, just that it's orthogonal to a hypersurface. Yeah. The obvious means. Yeah, this I actually don't remember, and I have written down somewhere that there's a, yes, Appendix B.3 of Wald's book is what I have written. That zero rotation is necessary and sufficient for the geodesic congruence to be hypersurface orthogonal, namely that there is a space-like hypersurface everywhere orthogonal to the vector field. So, well, this is called the, okay, so there are, by the way, there are nice resources. As you might imagine, this stuff is used even in fluid dynamics. This is general properties of flows. Okay, vector fields generate flows, and flows have an expansion and a shear. The word shear obviously comes from fluid dynamics. And the shear basically tells you that if I have some vectors moving in a plane, then the next plane to it, after some time, the geodesics here are not sitting next to these, but are slightly displacing like that, what you call shear. Rotation tells you that the geodesics sort of twist around each other, and that rotation can be removed, as I said, by choosing a hypersurface orthogonal congruence. So the congruence, I think that maybe I was too fast. The definition of hypersurface orthogonal is that there's always a hypersurface that is everywhere orthogonal to the vector field. So I think if it tries to rotate, somehow the intuition is that that won't happen. But for the details, you'll have to look at more. Maybe if I can find a simple proof, I'll tell you next time.
Meaning that every tau equal to constant hypersurface, this velocity of the geodesic
Yeah.
is not.
The velocity is normal to the, something like that. Yeah, I think that is
For
it.
every tau.
Yes, yes.
Is it for every tau, or does there have to exist one surface which is sufficient?
I think it's okay.
If there was one surface only, then you would have said omega equal to 0 maybe only on that.
That's correct. Yeah. No, I think hypersurface orthogonal is a more global statement. Okay, so we have 20 minutes left, and in this I will give you. So, are there any more questions? So, this set of we derived the Raychaudhuri equation for theta. There are analogous equations for sigma and omega. We are not going to use them in this course, but you can easily write them down yourself, and they might be useful for other applications. Yeah, there was a question.
Yeah, so this statement about hypersurface orthogonal, is it coordinate dependent?
It should not be. Everything we've done is not coordinate dependent. So, in fact, I told you the definition is there exists a space-like hypersurface that's everywhere orthogonal to the congruence. So, it didn't say anything about the specific time, but since he asked, I mean, since the congruence is parameterized by proper time, we could as well say that every tau equals constant. Okay. Now, so far we have been considering congruences in a bulk. So the way our congruence was thought of, you have geodesics that cut this space-like hypersurface in a point, and since this surface has d-1 dimensions, we are considering all the geodesics in all d-1 space-like directions, cutting in all the possible directions. So it's like a bundle. Okay, but sometimes, okay, first of all, if we were working in 1+1 dimensions, then obviously we would have only a plane. I mean, I don't mean a flat plane, but this surface would just reduce to actually it would reduce to a plane in the sense we would have the time-like geodesic this way and we would have one transverse direction. But in this general case, we can still pick a plane. So we just pick one direction arbitrarily and consider a subfamily of the congruence spanning a 2D or really 1+1D surface. And I'll explain why we want to do that. So for that, imagine that in this hypersurface, this was, let's say, x1 and that was x2 and there was some x3 like that. This is always time. Then I just arbitrarily pick one of these directions, x1, and I consider all geodesics which cut this at points which lie on a single smooth line on this hypersurface. So obviously, except in 1+1 dimensions where this is the whole congruence, in any other dimension it's like a subfamily of the congruence. Why are we doing this? Because this will enable us to compare neighboring geodesics. All this time we are focusing on one geodesic and what it does. But we never really talked about what neighboring geodesics do with respect to each other. And that's something we want to know. So this allows us to study neighboring.
Sir,
Yes.
in a geodesic congruence, we have a set of geodesics. So we have a set of velocity vectors.
Yes.
Does that set have a vector space structure associated? No.
No, because actually what happens is, you see, at any point you have these vectors on a general manifold form a vector space at any point. That means at one point I can take all the vectors which are tangent at that point and I can add and subtract them. That's a vector space. Now go to another point. At this new point I have a new tangent vector which might have been obtained from the previous one either by parallel transport or some other transport, but I can't add this vector to that vector. The vector here and the vector there live in completely different spaces. Technically they form together a tangent bundle. They are a section of the tangent bundle. They are not, that's not a vector space. Okay, good. So I'm going to consider such a parameter family, and the idea will be then that we have a coordinate tau which is a proper time this way, and we are going to choose a coordinate s which is like a separation coordinate this way, which is going to take us from one geodesic to another one. Okay, this coordinate, when I apply it in the space-like hypersurface, it will take the point of intersection here to another point of intersection. Then I can follow that point of intersection and I get a whole geodesic, which is the neighboring one to the original one. Okay, so we label the curves of interest in this family, actually the points in this family, as x nu. This is some coordinate system of tau and s, where if I go along tau I am going upwards, and if I go along s I am going along this 1+1D surface. Good. Now I can extend the tangent vector v mu also to be a function of t and s. What does this mean? For a fixed s, I am on a fixed geodesic, then v mu is v mu of tau, the tangent vector to that geodesic. For any different s, I am on a different geodesic, and then v mu of tau is the tangent vector to that one. So far we have been restricting to tangent vector to one geodesic. Now we have a family of tangent vectors to all the geodesics in this. This is what I mean. I don't literally mean there's some surface. I just mean that we consider tangent vectors to a one parameter family of geodesics out of the congruence, and of course tau still labels the point along it. And remember that tau is subject to translations and scaling, because I can always reparameterize an affine geodesic by shifting the origin of its parameter, and it remains affinely parameterized. So I could, for example, choose that at tau equals 0 for all s, I am on this hypersurface. Convenient choice. Yeah.
Is v mu still time-like?
Yeah, v mu is still time-like, and v mu is the tangent vector to a geodesic for every s. So it's still very much time-like. It doesn't point that way. Okay. In fact, because of that, we need to introduce another vector which points in s. So locally, we think of v mu as being d by d tau, and we need another vector which we want to think of as d by ds. So that's going to be a deviation vector. It's called deviation vector. And what we are going to do, since we are locally assuming that this purely takes me along tau without taking me also along s, and this purely takes me along s without taking me along tau, so I can say that these two commute, v mu and s mu commute as vector fields. And the formula for that is that the Lie derivative, the Lie bracket of them is 0 if you like, but the simpler explicit way to write it is that this is true. If I translate S along the geodesic, it's the same as if I translate V along the transverse direction. Sorry. Yes. So this is the statement v comma s equals 0. Yeah, s will be space-like. I think that's safe to say. Yes, it will be space-like. Good. Now we already have a name for this quantity. What is it? This is b. Good. And we already know something about b. So our goal now is to learn something about s. We don't have any equation for s. We are going to derive such an equation. Okay. Now the first thing to note is we said that the motion generated by v and s commute, but we didn't say that v dot s is necessarily 0. So the first thing to check is v dot s conserved as I translate along my geodesic, and therefore I am asking what is v mu del mu of v dot s. And of course we are now used to the calculation for such things, so that's v mu del mu of v nu times s nu plus v nu del mu of s nu. This is 0. That one, we use this equation, which says I can replace v mu del mu of s nu, so it becomes v nu, and then this I'm going to replace using that equation above, s mu del mu v nu. No, I did something wrong. What did I do wrong? S mu del mu v nu outside. I've done something terrible. What have I done? Good. No. I haven't done anything. V mu del. Sorry, I just wrote it wrong, I think. I don't know what's going on. Indices are such a nightmare in life. Yes, yeah. No, this is right. So this is B nu mu, V nu, S mu. Yeah. This is B nu mu, and it's contracted with one V, but B when contracted with V on any of its indices is 0, so this is 0. So whatever is the inner product V dot S, it survives parallel transport, it just always remains the same, which tempts us to make that inner product 0 if we can. And as usual, we'll see that it's sometimes easy to do and sometimes harder. And now I'm at the point where I can derive for you a very nice equation called the geodesic deviation equation. We'll use all the equations which are sitting above. And basically, is going to be the equation for the second derivative along the geodesic of this S vector. I mean, once you have an equation for first derivative of anything, look for the second derivative and you get something very interesting. We'll see that the second derivative equation carries in some sense more interesting information. So we are going to try and find what is gradient with respect to tau squared on S mu. And this is V mu, sorry, S alpha. So there's V mu del mu, V nu del nu S alpha. So first step is to use that equation that was there above to flip this and put S here and V here. This is the Lie bracket vanishing. So it's V mu del mu of S nu del nu S alpha. This is like a 5 or 6 line derivation, so it's a bit tedious, but all the steps are straightforward and I just like to do it explicitly on the board. The next step will be to expand it out. So one is V mu del mu S nu times del nu S alpha plus V mu S nu del nu S alpha.
So is that V mu?
Sorry, where?
No, it's alpha. V alpha should be there.
Ah.
Second line.
Yeah.
Second line.
The rightmost part.
This line, that one?
No, second line.
Second
Oh,
line.
this should be V, of course.
No,
No, this is not V.
Second line.
The
Second
S
line.
alpha
This
is-
line?
Yeah,
S
the
alpha
right.
to V
Last,
alpha.
The one carrying alpha index.
the last thing should be V alpha, not S.
Ah, of course. Thank you. Sorry. And then I'm here also. And here also. There's only one S, so the rule is one S and two V's in all equations. Sorry, I made an original sin and then I'm propagating. I think this looks much better. Good, thank you. Thank you. Okay, now, just for fun, we are again going to use that equation and flip these two. So S mu, this time I'll get it right. V mu. And in the second term, we are not going to do anything this time. Okay. But now, okay, good, that's good. We have flipped it. And now we are going to take this del mu out. So S mu is here. This del mu only acts on this V, but I'll take it to act on V nu del nu V alpha. This as well as this. To correct, I'll subtract the term when this acts on that. So minus S mu, V nu, del mu, V alpha. And then I have to still copy that term, which is plus V mu, S nu, del mu, V alpha. Now the first term is 0, geodesic equation. Here I will relabel, I'll call mu as nu and nu as mu. It will be safest to do it the way I have done it here. So V will have a mu and S will have a nu. So I'll relabel here. Yeah, dummy indices. So I get V mu, S nu, and then del mu, commutator del mu on V alpha. Wow, got so far. V mu, S nu, I got so far and I haven't made any mistakes yet. And the answer then is V mu, S nu, Riemann tensor, alpha, beta, mu nu, V, beta, no, yeah, beta, exactly. Okay, this was a bit of a tedious derivation, but we've reached the end, and we can write our equation finally as, I think the best way is to write it like this: del tau squared of S alpha is equal to, now I'm just going to rename indices to make it a little more straightforward to write. One up and these three, and then these three will be dotted with V mu, V nu and S rho. So the second derivative of S along the geodesic is the curvature tensor times S dotted with two geodesic tangent vectors V's. And this is a famous equation called the geodesic deviation equation. And any vector S that solves this is called a Jacobi vector. Of course, it's actually a vector field, so often in the literature you will see the term Jacobi field. Now notice that we had some initial motivation based on these coordinates tau and small s, but all that has gone. There's no mention of, I mean, obviously these depend on tau and s, but there's no sort of, how to say it, maybe, I mean, it's a covariant equation in a two-dimensional thing, but actually, I guess we could at this point, yeah, I think this is the point of having a Jacobi vector. We could now treat this as an equation in the manifold. We can just let V be a vector field along a geodesic congruence. That is a must, otherwise we don't get this. And I think the statement, I'll check if it's correct, is that any vector field S that satisfies this is a Jacobi vector. So we don't have to now think that it's necessarily depends only on these two parameters tau and s. Okay, because there will be an S vector which deviates the geodesic this way or that way or some other way. There will be all such S's, and we don't need to restrict our attention only to some particular one. And of course, it's very important that this appears in the equation, because as we know very well, the geometric properties of a manifold, and especially those connected with curvature, are embodied in the Riemann curvature tensor. The manifold is flat if and only if that tensor vanishes, and if it vanishes, then the transport of S is trivial, but if it doesn't, then it's non-trivial, and everything depends on what this tensor is.
So this is basically reflecting the fact that V and del by del tau and del by del has coming.
It originally reflected that fact, but I would say that this, once we have this equation, we don't need to, we assume that obviously to get this equation. So we introduced a coordinate small s in order to get this equation, but after we've got the equation, I think we don't need that coordinate anymore. Because it doesn't matter, see, that small s was a deviation in some particular direction, what I called a one parameter family of geodesics. But
it was normal to del by del.
yeah, that's fine. But there are many, there are d minus 1 such directions, normal to del by del tau. This equation will be true for all of them. Because I can just pick any one of them and I'll get this equation.
So can I think of the right hand side as being like a force law which covers nearby units? Because
Yeah, maybe.
so if we evaluate, let's say, the right hand side for weak fields, do we recover the 1 by r potential?
Yeah, good point. That might be true. Try it and let me know. That's a good point. So yeah, you could, for example, I don't know, you could just, I'm just trying to think what would be a simple example to do it in.
I mean, just take like a foliation, like you take some t and some x's,
Yeah.
and then just look at the like, small fluctuations and then make a spatial layer,
Yeah,
and then just evaluate this.
but it would depend on R, right? The Riemann tensor.
Yeah, but I was just wondering whether you recover like 1 by r square. I don't know.
So you would need a Riemann tensor which has some, the point is you don't get anything, right? If R is 0, you don't get 1 by R squared.
No, you need to consider small fluctuations around.
Okay. Small fluctuation, okay, thank you.
Yeah.
So good, so we could consider an R which is something like linearized approximation. That's worth trying, yeah, good idea, that's very nice. Yeah, okay, we are out of time already, in fact over time, but just a very quick statement before I close this section, and then we can move on to null congruences next time, properties of null congruences. It will be mostly similar to what I did here, and there will be a Raychaudhuri equation, but the key difference there, just to anticipate, is that we will have to not just define a space-like hypersurface, but we'll have to define a codimension 2 space-like surface. The one which earlier I said is at the intersection of 2 null hypersurfaces, and everything will take place on that d minus 2 dimensional surface from which 2 null directions go out. So that we'll do next time. But we had left one open question, given that we showed that the parallel transport of V dot S along a geodesic is 0, it means V dot S remains constant, but can I make that constant 0? It's not guaranteed that for an arbitrary choice of S, this constant will be 0. For example, you can right away see the ambiguity. I could shift S by an amount proportional to V. What will happen intuitively, V is going that way, S is going that way, and S plus something times V, this is not meant to be 3-dimensional, this is all in a plane, it just gets tilted up a bit. Okay, but the Lie bracket of V with S being 0 is still true for this guy, because Lie bracket of V with V is 0. Okay, so since I only assume that S satisfies Lie bracket with V is 0, any S will do like this. But as for example Walt points out very nicely, the V part is quite irrelevant. It's not the thing we want. It takes me again, so if this is a geodesic and this is a geodesic, this S and this S will take me to the same neighboring geodesic, but this one is a little bit wasting its time, while this one takes me only there. So it would be nice to have V dot S equals 0, and for time-like case, you can make it so, given an S, suppose V dot S is not 0, then what we do is we shift S to S prime of mu, which is equal to, we basically shift actually the parameter tau. what we do is we make an S-dependent constant shift of tau. So tau goes to tau minus alpha of S. So it's a constant shift as far as tau is concerned. So the geodesics remain affinely parameterized, but alpha varies at different S. Okay. Then S mu is going to go to S prime mu, which is equal to dx mu. This was the original definition, dx mu by ds, but now of tau prime and S. So this is going to give me dx mu by ds of tau and S plus dx mu by d tau. Actually, I should have written partial derivatives for these. Now the derivatives are all partial. So now, of course, I have to use chain rule, and here I use d tau by d s. And d tau and the shift in tau, which is s dependent, is that function alpha over there. Okay. And now I can see that this is my original S mu, and this is my vector V mu times d alpha by ds. So as I said, we are free to shift S by an amount V mu times some function. And now this new S, which is called S prime, I can make it orthogonal to V by saying that V dot S prime is V dot S, which I assumed was non-zero. V dot V is minus 1, so minus d alpha by ds. And now I can simply choose alpha to integrate this equation and set it to 0. So I'll just choose an alpha such that V dot S prime is 0. This shows me that there is an S prime which I can create, which is as good as S for being a deviation vector. It will satisfy the same equation and it's orthogonal to V. Okay, I'll stop here.